Okay guys, so this is what happened. A cat walked under the bridge and caused a failure. I'm going to do a series of videos here. I have no choice by default. This camera will only give me 29 minutes, and then it does another file or whatever limit it is, and it files it out. So I apologize for the part 1, part 2 that's going to be coming at you, part 4, whatever it is. You can't get more perfect than that. He's on number 10. That's the loads down number 10 that I was talking about right there. So that's number 10. Now the loads have been released. Let's see if they go back on again. Wow, what a terrible play. Anyway, let's jump right into this. There's he's right by the node. And let me release him a little bit. Brucey. So this is the scale, and I'm going to show you something kind of different for you guys now, to show you a different way to go about this. This is what we're going to look at here. I'm going to show you how I set up post tensioning for you guys. And it looks like we're back to scale, back to loads again, down 11 and 12. All right, Bruce, hit the road, boy. Move over, Bruce. Come on. He's not used to the collar. Brucey, he wants free of the collar. Brucey, you want free of the collar? All right, so let me go ahead and jump over here to this, what I'm going to show you here now. So bear with me. Don't want to do much editing. It takes forever now. I don't know what my software is doing, but it might take 10 hours to load up a video. So yeah, by then a lot of other people have already released the same data, but I'm still in processing mode at that point. So for fun, not for fun at all, I'm trying to help you visualize. Come on, Bruce. I'm going to need that. Let me go a different angle. I'm trying to help you guys visualize the post-tension members and columns and loading. So I just threw this on there. It's not this is not the scale, but it gives you an idea of what you're looking at. Let me flip the lens around and talk to you. So when they post-tensioned the structure initially, they did D1s. These two are D1s. And they did the transverse cables. They did not do the transverse cables. These would be the transverse. But if you look at the transverse cabling, it's still not underneath. A lot of times it doesn't fall directly underneath the nodes, the nodes. So you can see what's happening here. You see how I can push down around my post-tension, my transverse cables? How the loads are getting around them? Now what ties it together is the concrete and some reinforcement. But if it's not on top of it, it doesn't get the luxury of that format. What's happening is the concrete is being bonded to the transverse cable, but from underneath. So now the transverse cables are being pulled from underneath, not being. It creates tension in the concrete. This is tension in the concrete because they're not directly bonded between the two of these together. There's not a clamp here. The clamp is the concrete, and that clamp experiences forces between the two of them with some rebar holding it up, but that would be tension. I'm putting that bit of concrete right here on the tension, if you can imagine. Now let me zoom in on that and get you a better little idea of what we're looking at there. So imagine that. So this is missing it. So you can go down to the plans and look at them, but you still need the as-built, because Erica changed some plans for, maybe she put these right underneath there, so everything's like that now. But this is the transverse cables. These were not. I'm taking liberty with how I loop back here, so you engineers out there, don't get all freaked out. So let me go ahead and remove that. These are loose, right? So all these guys are loose when they go to post-tension. They do D1s and the canopy. Watch how I'm catching hell trying to keep it balanced, even though these are supposed to be tendon loaded the same, about 70% of their load. If you were just off just by a little bit with your profile, you can see where you're creating some reactions there's some moments that aren't in equilibrium. Now we go to the end of the deck here, and I add that same load. Let's get this same load here. between not these guys here. These aren't participating, just these two right there. You can see when you get closer to the diaphragm, if you will, the stability happens. It's more stability than out further out. Transverse cables aren't here either, but you still get more stability here. I'm not doing any magic tricks. It's still the same amount of tension throughout the whole cable, through the wires here. Except for now, of course, the dead load, the deflection is greater in the middle. So you can see that the same force is weaker in the middle, right? The deflection and cabling. Doo-doo, doo-doo, doo-doo. All right, so you get an idea of that. Now let's go ahead and add these in real quickly, and you're going to have to bear with me while I do this live because the editing, like I said. So all I'm going to do is pull these up and try to give them some more tension for you. Give them tension. They should almost all tension themselves uniformly because the way I wrapped it, but the friction around the screws are going to get me quite a bit. These are screws. Some of them are smooth shanked and some of them are not. So bear with me. Bear with me. Okay, almost there. Now, this is 6 on this side, and I don't know, what's that? Let's see if I can get 6 back on this side. Let me wrap it one more time. They're not spaced evenly. They're just, you know, so-so. They're so-so, so you're going to have to bear with me, like I said. Give me some liberty here. Give me some liberty or give me death. Alright, so in fact this one now looks like it's looping back around, doubling back on top of itself. Oops. Oh well. Yeah, I set this up pretty fast only a few minutes ago for you guys. I have a long detail one I was going to do, but I said, you know what, let me just give you a glimpse of it, and this would be like my dry run for a better one if I so choose to do a better one. But this is with no transverse cables. As you can see just imagine, let me get you down here. You can see how the forces don't make mercury out there unless you're using concrete. But you can imagine if this was concrete, this creates a moment in here that puts this in a load path that could probably create a crack down there, etc. So to get those forces equally over to all these members, I'm going to just take some liberty again, double down on that. What the heck? So, just to lock it down. The transverse cables transfer the loads over to these guys. Again, you see now it will stay in place. The center line, so there's no reason for me to put it out here. But you can imagine if once the loads are applied, you see the flexural thing going on there. Now, if these are all together, it's a theoretical moment you're looking at that this would happen. This is what that punching shear would look like if it could separate itself, but it can't. This is the upright, if you will, is connected at the canopy. It can't go down unless the canopy goes down. But ultimately, we see deflection, a failure right about here, let's call it, as it takes a new moment, a new profile in the cable. They can no longer recover with the concrete and the dead loads. That this wasn't designed to be able to transfer the loads with that defect, if you will, defect in engineering, let's call it. I don't know who you blame that on. Everybody, I would guess, everybody that's touched this structure that they just could not see that what they were doing is just so wrong. I'm going to expand this, believe it or not, to where it's going to be the canopy. I'll do a canopy. I'll get these lines properly, unless they, I need more time though, but I'll get it. So I'll add post-tensioning inside here. I'll put it close to scale. This is what so you guys, anybody want to beat me to it? You have at it. Have at it. You'll get you'll do better than me. I never get any more than few thousand hits. So if a YouTube person wants to have at it, beat me to it, and I'll give you a thumbs up. So this is just what we're looking at when you're looking at its raw format, if you will. Again, the concrete does play a major role in this, and reinforcement. I'm going to end it with this. Plays a major role, and I'll do more parts to it, as I said. If pushing down on here puts the concrete that's between these two tendons in stress and tension right there, so that it's a reverse thing. Even though it's encapsulated, if you will, bonded all as concrete, that's not what's really taking place here. It can't go down unless it's connected to the transverse cable. The transverse cables can't go down unless it's connected to the concrete, everything working together in unison. So you can imagine that's a weak point. Right here would be, if it was connected, would be one of the strongest points there are. They cross. And I guess you could find a stronger point than that, because this is, well, they're all equal. The strongest point probably be out here, believe it or not, because it's got the least amount of load on it. The most concentrated load's in the middle. So probably the strongest point is bridges out here on the outer edges, if you think about it in that capacity. It's a lot of theoretical thinking here, so you gotta. I might change my mind on that, but that's what you're hearing right real fast, off the cuff. See, it experienced the least amount of moment. Of course, it's getting as I said, a butterfly effect going on. But the concrete is in compression here now too, where it does not try to. I don't know the profile. I don't know what profile these damn things are in the deck. Where are they? Low, high in this concrete? They're 1 foot thick deck. Out here, they're out to another thickness. We need the as-builts. Okay, terminating video. Just want to give you guys something a little delicious to look at.